So the velocity of the left side particle at 2 seconds, and this is really important, only in the x direction, right? Because we know that we have gained downward motion because of gravity, but we're using something that's only described in one dimension where there are no external forces. So we're going to remember that that's how we're using it. So this is the x component, sideways component, right, the perpendicular to gravity component, at the final time, which is 2 seconds, and it's for the left side particle because we don't have a number 1 and number 2, we have a left and a right. And it's equal to the difference in the mass between the two particles times the velocity of the left side particle at 0 seconds in the x direction, right? So we got to multiply by this particular piece of information, plus 2 times the mass of the right side particle times the velocity of the right side particle at 0 seconds in the x direction, divide by the mass of the system. And it turns out if you stick in all these values, what you get is negative 5/2 meters per second, right? And that's the x direction. It's only in the x. So that means that, another thing you can do is from kinematics, right? We had a delta t of 2 seconds, an acceleration 10 meters per second squared down, right? So in 2 seconds, you're going to change velocity from whatever you had before by 2 times 10. So this is delta v in the y direction equals 2 seconds times 10 meters per second squared down. And so the change in the velocity is 2 times 10 is 20. So seconds times meters per second squared is just meters per second. Whoops. J hat, right? Because it's downwards, minus j hat. So what this means is that the velocity of the left side particle at 2 seconds in the y direction is equal to 20 meters per second minus j hat. So this is actually also secretly, right? You notice I did all of this without talking about left side or right side. But what left side and right side have in common is they both start with no y direction motion. And they both get 2 seconds of gain in the y direction to their motion. So this is actually also the y direction velocity of the right side particle 2 seconds later in the y direction. So it turns out to be that. But what you can get is that the velocity of the left side particle at the time 2 seconds is equal to, here's the y component and here's the x component, minus 5/2 I hat minus 20 j hat meters per second. That's the left side particle's velocity. We were able to get the motion of the left side particle. It was a mixture of some kinematics, but also with momentum of a system considerations. What I'd like to describe now is somewhat of a big picture. So this is going to look absurd, but here's the Earth And let's just say, for the purposes of argument, that the velocity of the Earth at 0 seconds is equal to 0. I know that's absurd. And the mass of the Earth, if you go look it up, it's kind of a crazy number. It's like 10 to the 25th kilograms, roughly. So the mass of the Earth is this absurdly large number. Up above the Earth are these two particles that are headed towards each other to have a collision, and that's what the case is, right? This is t equals to 0. So if I go 2 seconds later, what's interesting is these two particles will have collided and separated, but they fell down towards the Earth. So what they look like a little bit later is, it's actually, this particle has a really big, you could say momentum or velocity, sort of down to the left. That's the left side particle. And the right side particle, when you go solve it, it's also got sort of a steep down momentum as well, like this. They started, right, they used to be somewhere up here. That's where they used to be. And then they did this like thing where they went and bounced off each other. But let's think about the Earth. So the Earth, I'm going to draw it kind of in an absurd way. I'd like you to notice that what I've done is I've caused the Earth to go up a little bit. That is, whereas before it had a velocity equal to 0, afterwards the velocity of the Earth, 2 seconds later, it's not 0. And in fact, actually, let's think about this. Earlier in the problem, I showed you that the system, which is these two little particles right here, that system gained a momentum of negative 80 kilograms meters per second in the j-hat. That is, the system of little particles right here, it went from vertical momentum equal to 0 to vertical momentum equal to minus 80 units. Let me remove the little the vector symbol. So in the vertical direction, this system at t equals to 0 didn't have any momentum, or it had momentum equal to 0. After 2 seconds, the vertical momentum of the system changed into minus 80. The conservation of momentum is the fact that if the system was able to gain 80 units of momentum downwards, the Earth must have gained, so the momentum of the Earth in this vertical direction must have become plus 80 units. And the idea is the system here and the Earth, they have a combined change in momentum of nothing. So we could say that the momentum of the Earth in the vertical direction was equal to 0 at the early time. This is the 2 seconds time. So at t equals to 0, p vertical for the system plus the Earth is equal to 0. And at t equals to 2 seconds, the vertical momentum of the system plus the Earth is equal to, well, the system has minus 80 units, and the Earth will have plus 80 units because they had an internal interaction due to gravity, right? it's still zero. Momentum is never created or destroyed. What the idea is like I started here with 0 and I end here with 0. If I think that momentum shows up out of nowhere, look at this. It looks like the system gained a bunch of downwards momentum. You should never assume that it came from nowhere. You should always assume that that means that the external world, something external, must have also changed its momentum. And it must have changed its momentum such that there is an overall conservation of momentum. What moves momentum around is external force. External force moves momentum around. Well, maybe better to say a force of any type that gets to act for any time at all, such that there's an impulse. Impulse is the clue that momentum changes hands, changes ownership.